Hello dear friends, welcome to my channel. Today's discussions is quantum physics. What are Bras and Bra-Ket notations? This episode I want to introduce another fundamental object in quantum mechanics, the bra. I also want to really dig into bra-ket notations and justify my claim that it is incredibly bra-ket notations. Powerful and useful. So to begin introducing bras, let's look at an example in the vector space of R square. An example in the vector space R square is 1, 1, 4. I am going to define a very simple linear map which called Lx. What it does is it takes in a vector and speeds out whatever its x components. So this vector has a component of 3 along the x direction. So this map would return this vector has a component of 1. Okay, is equal to 3 and the component Lx minus 1 comma 9 equals to minus 1. Okay, so this vector has component of minus 1 along the x directions, so this map would return minus 1. You can check that this is indeed a linear map. In other words, it justifies the following properties. Let's understand what is the linear map. Linear map is Lx v plus w is equal to Lx v plus Lx w. Okay, and Lx c v equals to c into Lx into v. Fundamentally, this map takes in an element of our vector space and returns a single scalar number. So that is Lx v equals to k. Okay, we have a special number for maps that do this. They are called linear functional. Special map that's called linear functional definition. A linear functional is a is any linear map L that goes the vector space to a scalar number. So LV tends to C. Okay, which may be real or complex. Okay, it may be real or complex. So friends, basically it's any linear maps that takes in a vector and spits out a number. Now that we know what a linear functional is, let's move back to R square and figure out what the matrix for Lx looks like. Okay, so our function is f such that R square to R. We know Lx takes us from the two-dimensional dimensions down to one dimension. Okay, so we know we will have 1 plus 2 matrix. We will have 1 plus 2 matrix. Okay, the first column tells us where the x basis vector goes. So plugging in 1 comma 0, which has a component of one of the x-axis, we get 1. Okay, just plugging 1 comma 0, we get 1. Okay, the next column tells us where the y basis vector goes. So Lx, just plugging this 0 1, we get the value 0, and our Lx value is 1 0. This is our Lx. Okay, just putting this value in here. Okay, so this is matrix of the linear functional. This is matrix of linear functional. So we see that we get what's called a row matrix. It is essentially a column vector on each side, and what it does, it takes in a column vector and spits out a number. Let's take a step back. Okay, step back is, remember that in R square a linear functional is a linear map that takes us from two dimensional to one dimension. Okay, R square to R1. This, by definition, this means that all linear functional in R square are represented by 1 by 2. Okay, this way represented. And so the set of all linear functional in R square consists of the set of all row matrix. Set of all row matrix. So all linear functional is this way, all linear functional this way, 1 comma 0, a comma b, 3 comma minus 2. Okay, much like column vectors, this set of all row matrices actually forms its own vector space. Seriously check all the conditions, they work. This vector space is known as dual vector space. Okay, this vector space known as dual vector space. What is the dual vector space? Dual vector space is set of all linear functions. Okay, I will discuss very soon that what is dual space. Take your vector space of column and vectors and turn them on their sides. So suppose my vector space is a comma b, then it turns on this way, a comma ab. So it is dual vector space, it is vector space. Okay. What you get is the dual vector space of linear functionals. This has been specific to R square, but the dual space is a very useful concept in abstract vector spaces. Formally, we define the dual space as follows. Given a vector space V, the dual space V stars. Okay. So given the definitions of, now I discuss definitions of dual space. So V, given a vector space V and dual space is V star. V star is dual space. This is dual space and this is vector space. Okay. So clear. So vector space. So V stars is the vector space of all linear functional. Okay. All linear functional is okay. So L live in V star. Okay. So all linear functional L live in V star. Although this is an abstract definition, keep the intuitions that the dual space is a analogous to the spaces of low matrices. Our goal is to build a mathematical model for the real world, and in the end we want to be able to extract values and predictions from it. For example, given our quantum state, okay, this is my given quantum state. Given quantum state, we want the probability to get an energy 3 electron volt. Okay, energy equals to 3 electron volt, and we want to average positions we expect in this state. To get this, we have to go from the quantum state to number, and so we know that a linear functional is involved here somewhere. We have to use linear functional in our quantum theory. In fact, linear functionals are so important that we will ascribe a special symbol for them in quantum mechanics, symbol called a bra, written as backward ket. Okay, backward ket. This is bra. Okay, bra, and this is operator. Remember that this is a linear functional, so this should be solution as the operator that act on a ket. Okay, an operator act on a ket and returns a number possibly complex. So it is act on a ket. Ket is shy, and this is the C, which may be complex. It is maybe complex or real. Okay. So as we stated before this, bras live in the Hilbert dual space. So bra lives in Hilbert dual space. Okay, so when we put a bra and ket together to get a number, it looks suspiciously like inner product in this notation. So equals to, you can write high shy. Okay, so we have made zero mention of the inner product. Let's go back to our LX operator in R square. So what is my linear function Lx is equal to 1, 0. Lx acts on a column vector. Okay, Lx acts on a column vector. So Lx 1, 0 into a b equals to 1 dot a plus 0 dot b. It can be written as 2 vector dot product. Okay, dot product of 2 vectors ab. Okay, so in fact when a linear functional in R square acts on any vector, it can be written equivalently as a dot product with the corresponding column vector. This is actually a very deep and a general mathematical fact rooted within something called raised representations theorem. Okay, this sounds kind of daunting, but it's just it as a theorem about what we discussed. So let's start to discuss raised representations theorem for any linear functional null L phi, linear functional L phi. The action of L phi is the action of L phi. L phi is equivalent to taking the inner taking the inner product with some unique vector phi, with some unit vector phi. Okay, so L phi v equals to inner product phi comma v. Okay, so friends, you can get this proof from Google or your book, your textbook. Okay, I just want to discuss only raised representations theorem. What is raised representation theorem? Okay, so I hope you can understand what I want to say. So you see my previous example LXV, this example, if you see that LXV is equal to 1, 0 and V. Okay, inner product. Okay, in inner product of phi and v, phi is 1, 0 and v is a, b, or any arbitrary. Okay, so why we choose our suggestive notation for a bra? Suggestive notation for a bra. A bra is just a flipped cat, okay, because the action of the bra linear functional is mathematically equivalent to taking the inner product with that kit. So I just write bra is the bra is flipped kit, okay. So this notation for bras and kits and inner product is collectively known as bra-ket notations. So this is the bra and this is the collectively is called bra-ket notation. Okay, bra-ket notation also is called Dirac notations. Okay, so he was the first to use it in quantum mechanics. So why this notation is powerful? Next question, why this notation is why this notation is powerful? It has the range representation theorem backed right into it. You can break apart inner products and put together bras and kits. You can be rest assured that whatever you get still makes mathematical sense. All because of the raised representations theorem. Although a bra and the linear product are formally completely different mathematical entities. Now equals to this phi psi. Okay, bra-ket notation makes their connection absolutely seamless. The raised representations theorem is working hard behind the senses. Example, we have an orthonormal basis in our vector space and we expend an arbitrary. So we expand quantum state in this orthonormal basis psi equals to I and Ci AI. Okay. So calculate coefficient as follows. Okay. You know how to calculate the coefficient in my Schrodinger wave equations. First correction I have already discussed. It. Okay. So calculate coefficient as follows and plug in this expression for all the coefficients. Okay, this way I can write. Okay, so let's move inner product to the front. Okay, so what we get? We get AI. Okay, here is the power of bra-ket notation. We can break apart the inner product. So now we have this operator being Okay, so apply to the ket psi. Okay, apply to the ket psi. Okay, so we can break apart, so we can write this way: ai and ai. Okay, now we can write this way: so this way we can write. Take a look at the right hand side. We have summed operator that when acted on psi returns psi. This means that we have just proven that for any orthonormal basis, the sum must be equal to the identity operator. What is the identity operator? Identity operator is this way. This expression is called resolutions of the identity. So now psi is equal to summation ci ai. Note how bracket notation made it really easy to move things normal. So friends, I hope I can clear the concept, and I will discuss a lot of about this. Thanks for watching, because this is very helpful for quantum mechanics learner. And please, I will please view my total work. Okay, whatever I have done. Okay, thanks for watching.